Let's continue discussion on symbol table now. See, we have discussed our introductory narration is going to end. We have done a brisk walkthrough through all these modules of compiler, and we have discussed till code generation. Now, what is missing is two things. One is symbol table. We have seen in our earlier diagram that every module of compiler refers to a symbol table. Specifically speaking, symbol table is getting generated in the analysis phase of a compiler, front end part. Lexical analysis, syntax analysis, and semantic analysis modules, it generates a symbol table for a particular program, and they adds data and they use that data also, all these modules. Once the intermediate code is produced in the backend part, that is the code optimization and compilation code generation part, symbol table is heavily referred by those two modules. So symbol table is in demand by all these modules. That's what you can see here. All these modules will see source program, it generates a token stream, all this. See, everywhere it is symbol table is getting referred in all these phases, both the backend and front end. And now, what is a symbol table and why it is to be kept? Remember that the responsibility of a compiler is to generate the source code. Excuse me, it is not. It is to generate the target code for a source program. Program has to work in a computer system. Programmer can define any kind of variables, any kind of data structures that is supported by the program, and all those data structures will have to be accommodated memory. A simple variable like int I is a data structure, primitive data structures. There will be compressed data structures, user defined data structures that are statically defined and dynamically defined. So we have a hell of all these. How proper memory allocations can be done? How properly these memory references can be represented? These jobs are done with the help of a symbol table. All identifiers will be added to symbol table. What's an identifier? We have learned that a variable name is an identifier. A function name is an identifier. Labels are identifiers. Actual and formal arguments are identifiers. Everything is an identifier. All these identifiers will have to be kept somewhere, not just the name of that. Every identifier has a semantic aspects. Int I, when you say int I is not just a variable. I has a name I. It has a data type called int. It has a maximum width of ranges of values, minimum and maximum value. Whether it is signed or unsigned, values can be kept in I. What is the scope of I? Is it a global variable or other kinds of variables? So all these things will have to be recorded properly. So right from the lexical analysis to semantic analysis. Whenever these data are available, those data will be gathered and stored in a simple table as attribute values. See the attributes, data type, its width and scope. There are a lot of attributes. We have taken only a very few for, we are just beginning now. Now, the attributes are added not in the lexical phase alone. All in the analysis phase, more details will be added. Now, again, we'll go back to some definitions. Single pass and multi-pass compilers. What do you mean by a single pass compiler? See, compiler has these modules. We have learned that. But when a single pass compiler is done, there will be only one module that comprises of all these functionalities. So it has only one input, your program, and directly it produces the output. All these modules are not written, designed separately. A single pass compiler will be having an entire monolithic module. Now, it is considered to be faster and smaller than a multi-pass compiler because you have only one module. There are no intermediate results. It generates the source code as such. No, the low-level machine code. But in terms of efficiency, it is considered as less efficient than a so-called multi-pass compiler because we have learned that when we go for modules, it makes our works easier. Suppose that we have a separate module for lexical analysis and syntax analysis, and later we find a small bug in lexical analysis. What we can do? We can just modify this lexical analysis without affecting other modules. It's agility in modular programming. And this agility is lost when you have a single pass compiler, but it is faster and smaller than multi-pass compilers. Now, in a multi-pass compiler, single pass you don't have different modules, but in multi-pass you have at least different two passes. See, in one pass you get an intermediate code, a second pass you get the low-level language. So here we have combined the analysis part into one module, first pass, and the second pass, backend pass, is made into separate sections. And there can be different modules for code optimization. So like that, depending upon the compiler designer, designing process, the team who designs that, there can be several passes of compilation. And when we go for that, it inherits the benefits of modular programming. So people may ask you what you mean by multi-pass and single pass compilers, and they may ask you to differentiate them also. That's why we have mentioned them. With this we end this introductory concepts.